absolutely destroying the lessons, and I promised you we would have a week of relative ease. This is your week of relative ease. For this first lecture, we're going to talk about power. That's it. We're going to talk about power. Let's get through it. I promise it's going to be quick. Let's rock and roll. All right, quickly, what is power? We'll talk about that. The forms of power, scratch that for right now. Power in a circuit, we're going to do a quick example and do some calculations, and we're going to show calculating power in a couple of different derivatives. Let's get into it with what is power. Power is the measure of how much work can be performed over a given amount of time. We measure power in watts or wattage, and the universal symbol for power in America is the capital W. Before we can get more detailed into what power is, we need to take a step back and figure out what we know. So voltage, we know voltage is a specific amount of work or potential energy per unit charge. Remember how we used a coulomb as the standard candle for the different aspects of our circuit, whether that be voltage, current, or resistance? Well, over that per unit charge, that's what we're talking about, that standard candle, whatever that may be. And then we have current, which is the rate at which electric charges move through a conductor. But let's dig a little bit deeper. Voltage, what we're really talking about is a force, right? A pressure in our circuit. And it's also a potential that the circuit has, effort that can be exerted within a system. Whereas when we're talking about current, we're talking about a quantity or a volume, right? The number of electrons, that large number of electrons. But inherently, we're talking about time. It implies time because we're talking about what the quantity is over a given period of time. So let's throw those together really quickly. When we're considering that voltage and current, if you looked at any facets of physics, we could be talking about intensity times direction or potential times application. What we see is work is being a product of force and volume, or work is a product of potential and quantity. What we're really saying is power is equal to force times volume, right? It's the force of electrons and the volume of electrons. And if we want to express that mathematically, super simple. Power is equal to current times voltage, or power is equal to I times V. Or if you want to go with electromotive force, then you can say pi. Power is equal to current, or I times E. Super simple. Like I said, we're going to jump into a quick demonstration, and we have a sample circuit here. A simple circuit that has a 12-volt power source, and it's attached with a light bulb that's offering 4 ohms of resistance. Knowing what we know now, that we can use PIV or pi, how much power is the light bulb emitting? Well, let's jump into it and figure it out. All right, we have our crudely drawn but accurate circuit, and let's take a look at what we got. We've got 12 volts on our source. We have an unknown current, and we know that our light bulb is offering 4 ohms of resistance. First thing we've got to do is we've got to take a look at Ohm's law and figure out what variables do we have that we need to solve for. Let's whip out our VIR, because we know voltage is equal to current times resistance. Let's take a look. We've got 12 for our voltage is equal to, here's our unknown I, and 4 ohms of resistance. We got to isolate I by itself, so we will divide by 4 on both sides, meaning that our current is equal to 3 amps. Let's honor that bad boy, and let's throw 3 amps in our current. Okay, using Ohm's law, we figured out the 3 tenets that we need for our circuit. We've got our source, our voltage, we've got our amperage, like the volume of electrons, and then we have a resistance that's inherent in the light bulb. All right, well, what's next? Break out our newfound equation, which is pi, or and figure this one out. And this one's super simple. So we've got power, let's bring that down, and it's equal to our current, 3 amps, times our voltage, which is 12. Let's multiply those together. We've got 36. The power being emitted, or the wattage being emitted by this light bulb, is actually 36 watts. And that is it. Power in action. Now, that being said, there are a few derivatives from this equation. I wouldn't worry about it too much because I'm going to give you a cheat sheet and you guys are going to study and you're going to be fine. So if you wanted to break all of the different derivatives down, knowing what we know about Ohm's law and how we can now calculate wattage, this is what it looks like. We've got a column right here, a row for how to calculate resistance, amperage, voltage, and of course wattage. Now I'll give you guys a cheat sheet so you can study this, but I guarantee you throw any of the figures or values in here through those derivatives and you'll get the same answer depending on what you're looking for. So give it a shot, take a couple. Ones that I would focus for on the test, probably this one in the middle right here, resistance is equal to voltage squared over power. You'll probably see that one. The current is equal to voltage over resistance. That's an old goodie right there. And I would keep an eye out for power, or wattage is equal to current squared times resistance. Alright guys, real simple. See you in the next lecture.